Thanks everybody for joining us today. Again, like Cindy said, my name is Marty Candice. I work in sort of the HPC user services group here at SDSC. So if you're ever using one of our systems, we're usually the team that's responding to your emails and trying to help you use the systems for your research. This project here, Complex, is one of our cyber training programs. We're sort of, I think this is our third talk of this year. So it's been going on. So this is our third year of the program. And this talk today is on uh, uh, sort of the first talk in our batch computing series. We sort of have sort of three different topical sessions on this topic, and today is working with the Linux scheduler. So hopefully that's the talk you're here for, and we'll get started. If you're not familiar with the complex program, and maybe this is your first time joining us, just a quick overview. So the complex program is a cyber training program funded by NSF, and the idea is we're trying to cover topics that are not necessarily programming specific, but are the sort of non-programming skills and techniques and concepts that you need to understand to use the advanced cyber infrastructure, high performance computing resources, supercomputers that NSF funds to help you do your work. And so that's sort of the idea. So we have a bunch of different topics. We've already had our parallel computing concepts talk in early mid January. We had another one on intermediate Linux recently. We do shell scripting, batch and interactive computing, data management, and a bunch of other things. So that's sort of the idea of the program, if you're not familiar. As I mentioned already, this is sort of the first talk in the batch computing series that I've sort of put together for Complex. So today is really about sort of giving you an idea of what a scheduler is by looking at the Linux scheduler and sort of running some programs and understanding what processes and threads are. We covered what processes and threads are a little bit in our parallel computing concepts talk if you attended. I'll review that briefly today and discuss a little bit about, and we'll walk through some exercises that sort of hopefully will start giving you like a practical feel for what a process is and how you interact with it when you're working on any of the systems which are all Linux based. So that's sort of why we're talking about the Linux scheduler. But there are links here. So the highlighted yellow underline are actually URLs to past versions of this talk. So it should link out, hopefully. I didn't have time to double check today that the links are still good. If they're not, please let me know, but we'll try to fix those if they're not. But as Cindy has put all the links in the chats, probably we have lots of links there. So yeah, there's a GitHub repo associated with Complex. We have all of the PDF versions of the latest version of the slides online, and all of the recordings of the webinars eventually end up on YouTube, so you can find them there as well. If any of these links are broken. So okay, so today, so what's the goal today? So the goal today is really to review the concept of what a process is, what a thread is, and then start doing some more practical hands-on exercises to get you familiar with how to interact with processes and threads on Linux systems, because all of HPC and advanced cyber infrastructure basically runs on Linux. So if you're not familiar with running Linux or using the command line, this is sort of your introduction to sort of what it looks like when you're running a program on these systems and sort of some of the things that you might have to do or want to check or look at as you're running the programs on these systems. So we'll talk about the top command. We'll also look at sort of process priorities and things like that. So that's sort of the goal of this talk, right? To sort of give you that sort of conceptual feel for what a process is, what a thread is, and how you can start interacting with them on real systems. So also have a couple of just the prerequisites here, which are basically just the talks that we've already had this year, which other than we've split up the intermediate Linux and shell scripting. So there are two versions of the talks now. There's two talks now out of that, but that's kind of the idea of what you sort of should sort of have already seen before. If not, you can feel free to go back and review that material. Okay, so this is sort of the overview of the talk. Again, most of this talk, I'm trying to get more time into doing only hands-on and walking you through some of the exercises you can do later, and showing you sort of how to begin that process. But I'll do a quick overview of the high-level concepts of sort of HP system architecture and scheduling. Again, what is process, what is thread, which were again covered in the parallel computing concepts talk as well, and just sort of try to relate that to the process scheduling and how that occurs on these systems. And then we'll go into the demonstrations with sort of example programs. And as I think Cindy mentioned, complex, how it's structured, usually all the webinars are about an hour, and then we stop recording and then just do sort of Q&A for half an hour if you can stick around and have extra time to ask questions. Okay, so HP system architecture. So this is sort of the detailed cartoon diagram of what a supercomputer looks like that you might access on at the different centers around the country. So this is Expanse at SDSC. This is our main production supercomputer right now. Now in its fifth year. So it's a bit of an older system that you'll find on available from the Access program, which is the NSF program that's sort of the umbrella organization over the different resources that are funded and where you can apply for time on these systems. But yeah, there's a couple different ways to sort of understand sort of how these systems are put together. Most of them have a very similar structure. There's more specialized resources these days, but the big production supercomputers all kind of look similar these days, where you have a bunch of racks. These are sort of the refrigerator size cabinets that you see in the diagram here on the left. Each of those cabinets has a different sort of slots where you put the individual compute nodes in the racks. There's usually a bunch of racks that are then all linked together through the networking so that you can communicate between all of the different compute nodes from all the racks. You can usually reach every point in the cluster from any given node. And that means you also usually have some sort of specialized high bandwidth, low latency interconnect. We have, for example, InfiniBand on Expanse. But in addition to the compute nodes where your jobs and your research will run, you also have different specialized storage systems. For example, on Expanse, we have a Lustre file system, which is kind of good for really large reads and writes if you're, say, doing like weather simulations or something like that. Then we also have object storage in a Ceph file system, which is a different type of storage system that is more common that you'll find on systems these days. Then there's a host of management servers and things and different specialized connections to different research networks. And so there's a complicated picture when you start looking down at the details. But there's a conceptual cartoon that, it's useful to keep in mind when you are thinking about how you're interacting with any of these systems today. And that's right. That's one more slide. I'll come back to that conceptual sort of cartoon in a minute. This is what sort of an additional sort of lower level detail. This is if, as I said, each of those slots in the different racks are a compute node. This is sort of what one of those compute nodes look like, or people might refer to them as blades sometimes. But this is actually our sort of what our specific model of our GPU compute nodes look like. So our GPU accelerated compute nodes on Expanse. This is the exact model from Dell. And so you can see there's all sorts of details inside the node too. Most of these resource compute nodes usually have sort of two CPU sockets. So you have two CPU processors. When you then add in, say, GPUs, if you need GPU accelerated computing, you usually have these days 4 to 8 GPUs in a given node sometimes. But again, just like the networking at the sort of rack scale and the system side scale, even within the compute nodes themselves, you can see here in the Dell information sheet, there's actual different configurations of how the CPUs and GPUs are connected together inside the node. So, the details at the end of the day matter for your performance and maybe your application, if you really get down into those details. So there's a lot to learn if you're not familiar with this, but this is sort of, a place to start. It's always anytime you get into a new area and don't have quite the expertise, there's a lot of terminology and definitions to learn about. But this is sort of, understanding the different pieces of an HPC system is quite useful when you start trying to understand how your code is running on them. But this is the conceptual model I was sort of talking about. And it's like every time you are interacting with one of these HPC systems, usually you have a few different things to sort of keep in mind. There are login nodes, there are compute nodes, there are the internal networks I mentioned. There's the shared file systems, the special file systems that you have access to store your data. And then there's like a set of management nodes, which you interact with because there's software that's running there, like the scheduler that we'll talk about in the batch computing series. Um, but this is sort of the mental model that sort of I use for myself, right? When I'm thinking about like what does any HPC system look like, this is basically kind of what it looks like, where the login nodes are the front door where you actually access the system. Your jobs run out on the compute nodes. They may or may not use the internal networks, sort of communicate between the compute nodes, or just use those networks to communicate to the file systems and the storage. And the management nodes is sort of where the scheduler lives, and you'll be interacting with that when you submit jobs to the system. So anyway, this is just kind of an overview of what an HPC system looks like in sort of a mental model. So we're talking about batch computing, right? So we'll go over this again in the second, in more detail in the second talk in this series about what a batch job is. But essentially, again, one of the prerequisites for this was a shell script. So a batch job is really just a shell script that you run on one of these high performance computing systems that's got a little bit of extra information that tells the scheduler, the batch scheduler on the system, where you want your job to run, right? And what resources it needs. And so that's all that this is a shell script, but it just with some special features that we'll talk about in the second version of this talk to specify what you need to run the code that you want the system to run for you. And the batch job scheduler is this piece of management software you'll find on these systems that essentially takes your job script and tries to figure out where your job will run and when it'll run, because essentially it's like the air traffic controller, essentially, of the system, right? If there's a bunch of users, they submit a bunch of jobs, there's, usually more jobs that are requesting more resources from the system than are available at any given time. So the scheduler is the command and control that decides who goes where and when you get access to the resources you need, right? So that's sort of another good mental model to have how these systems work. And the most common batch job scheduler out there these days on most systems is the Slurm scheduler. I won't talk too much about that today, but this is what we'll use next time in part 2 to start learning how to run batch jobs and batch job scripts. But at the end of the day, right, we're talking about running batch jobs. Batch jobs are essentially, the idea is you want to run a prescripted set of commands without any sort of interaction from the user, right? You kind of want to set it and forget it, like set it up, let it run, submit to the scheduler, have it manage everything, get your research out, right? But at the end of the day, at the very fundamental level, right, you want to run a program, as in the diagram, that has a bunch of instructions, right? That program will eventually get loaded into memory on the real compute node you land on. There are things that then the program looks like and how it's abstracted to the operating system. And these are what are processes and threads. And at the end of the day, right, every program that you want to run on these systems, right, it's they also, just like the batch job scheduler is trying to request compute nodes and storage resources, even on the individual node level, just on the single computer, even on your laptop, right? Um, there's always multiple programs that are running that are competing for the CPU and memory resources, maybe GPU resources on a single compute node, right? Or even just your laptop, right? And so one key part of that is an individual process scheduler that is running in your operating system, right? And that's the idea for today's talk, to look at how starting a program creates these processes and how we can look at it and how you can sort of play around with like create and kill and change priorities of how these programs run, right? Because at the end of the day, when you go back next time in the batch computing 2 talk next time, right, we start talking about that Slurm scheduler, which is running across the whole system that you might be interacting with the HPC system, right? You also still need to understand that at the end of the day, the Slurm scheduler will just drop your program into a given node, and then the node will use the operating system scheduler to run your job essentially as sort of the thing that's controlling the local execution of any process that you launch. So that's sort of the connection between the two, the large scale sort of distributed scheduler versus the sort of OS level schedulers we'll talk about today. So just a quick, so yeah, I see there's a little bit of chat in the meeting chat, and that might be questions. I think we have Nicole, and yeah, it looks like Bob's here, who can help answer those. And the slides here are pretty short. I'm almost done with just sort of the definitions before we jump into the demonstrations and sort of the hands-on that you can do on your own computer. But yeah, I'll come back to that the chat once I'm through these slides before we jump into the demos. So yeah, processes and threads. So these are the two key concepts that we're gonna try to look at with the hands-on demonstration. But again, the definition that was also used in the parallel computing concepts talk, a process is just really an instance of your program that you're running, right? It has, so anytime you start an application, there is a process that's running on the system where you've initiated that execution, right? And every process has its own sort of memory and access to different resources on the system, right? So this could be also, as stated here, file descriptors, which are just kind of ways to allocate access to writing and reading files. This is just sort of the abstraction that exists in most of the operating systems you'll use these today. Whereas a thread is a lightweight entity abstraction that executes inside of a process. So every process has at least one thread. But if you do have multiple threads, the threads within that process can actually access the same resources from within that process, right? So this is sort of what was, I think, covered in the parallel computing concepts. We have a shared memory model when you're talking about threads. So threads can access the same variables at the same time, essentially, right? Effectively, right? And if you update that variable, that value changes for every single thread in that process. Whereas you can have multi-process applications where you have multiple processes, so each has its own different memory. And so if you actually want to have some variable that's maintained consistently across the whole application, you actually then have to explicitly exchange those values and synchronize them yourself, right? Whereas the shared memory model is really actually accessing the same location of memory usually. So that's the difference between processes, right? So the process is really just every time you start a program, you have at least one process. Right? You might have more, but most of the time, it's most people usually have at least one, right? And then within that, you have threads that can be used for some parallelization as well, but it's in this shared memory model versus a multi-process model. So that's kind of the difference. There's some nice links here also that Bob has in his talk that I've kept here for more discussion on what the difference is between a processor. In particular, I think the Stack Overflow one's pretty good. If the QB one, yeah, it's got they've got a lot of pop-up ads these days, I think, so it might not be as appealing to look at. Um, okay, okay, yeah, and so what are so this slide is just highlighting kind of the advantages, disadvantages, differences in terms of like performance-wise, what processes and threads are. So yeah, processes are sort of again more heavyweight, so they incur more overhead in terms of the resources. Every time you start a process, it's a little bit more resource intensive, so it's sort of the time to start up a process might be more, right, for your application. But again, yeah, they're sort of more flexible and you can use distributed memory models, so you can actually have applications running across multiple compute nodes, not just a single compute node. Whereas the threaded shared memory model, it's usually everything has to be in a single compute node. But yeah, there's usually less overhead, and threaded codes are usually easier to create with a lot of the application programming interfaces that are out these days. But yeah, and so it saves on memory, obviously. So it's kind of the advantage, disadvantage of the two types of models between distributed and shared. So yeah, again, why do we care? I think I probably already said this as well, but yeah, so distributed memory applications are the types of applications you can really scale across multiple nodes. So when you hear about like applications running across hundreds of thousands of cores, those are going to be distributed memory applications. Shared memory applications, a, a lot of the applications we just probably run on our daily laptop are probably multi-threaded applications, right? Because most laptops these days, personal computers have multiple CPU cores, so you have access to, multiple CPUs. So why not have applications take advantage of the ability to do sort of a multi-threading to improve performance? Most applications do. Um, but there's also the ability to do hybrid applications where you have both distributed and shared memory models in the same application. And so this is very common as well these days for scientific codes, at least. Uh, yeah, I think that's all I needed to say here. I think, yeah, I don't think I have anything else there. Okay, so a couple things. So this is what we'll be looking at today this is just a quick overview of some of the tools that we might take a quick look at today in some of the demos. When you start wanting to uh, get a feel for what processes and threads look like, this is usually the tool you'll hear about from most people, right? So this is top. So this is, top, I think the acronym is sort of table of processes or something like that. I think that's the actual uh, meaning of top. But essentially, it's a way to look at the different processes that are and threads that are running on a given Linux system that you have access to, right? So it's a local look at what's going on the system. And this is how you can sort of inspect if your application might be running properly. Is it using the right amount of cores, the right amount of memory that you're expecting? It just gives you a way to access a ton of information about the different applications that are running. And it's sort of just a staple of when you start using the command line interface to interact with system. This is one of the tools you'll want to start learning how to use. And so we'll look at that today when we start looking at running the demonstration jobs. An alternative, which is probably newer and a bit more a little bit more graphical and obviously has some coloring and different type of interface, but basically the same information for the most part, is HTOP. So it's just another way to view processes. So you learn top or HTOP. I usually use top still myself, but there's probably good reasons to use one or the other for different inspections. Yeah, let me see. Yeah. I use HTOP if I just want a visual quick look, because you can see here there's like a layout of the number of CPUs that are on the system or CPU cores, and sometimes it's easy to you want to actually know where is my program running, like physically, which core is it on, or what cores is it on, right? And that's what HTOP is. When I use it, that's what I use it for. Okay, and that's the end of sort of the general definitions and overview before we jump into the examples. And so I will stop here, and then we'll talk about the example program we'll use and where to find some of the exercises with the example input and output. But let me go through and check the chat and the questions.
Marty,
So
there was only
Sean,
one question,
okay,
from Sean.
yeah,
The
okay,
rest was me,
about
so.
TSSC. Yeah, so the concepts, yeah, are definitely the same. The this model. Oop, I'm going too fast from my screen. Okay. Yeah, yeah, Sean. I mean, I think the concepts today are good for almost any modern computer, right? That you have access to, right? On TSCC, like the nodes on TSCC will look a lot like the Expanse nodes here, right? TSCC has GPU nodes as well, but again, most HPC compute nodes, even if they don't have GPUs, usually have two CPU sockets with each CPU socket and processor has multiple cores. So the mental model and the actual physical layout of any compute node is kind of the same, unless you're dealing with some specialized hardware. And there are a lot of new specialized chips and systems out there that are very different than sort of the standard high performance computing compute node. But yeah, TSCC is kind of the same as Expanse in terms of the you know very typical HPC type of system. TSCC might not be as optimized maybe on the multi-node aspects, but on at least on the compute node level, yeah, it kind of looks the same. What else do I have? But yeah, so today, since there's no other questions, the exercises are actually really meant for you to be able to do them on any computer you have access to, including your laptop. Like I'm going to run all the examples on my laptop right now while I walk through as many as I can in the next, what do I have, 25 minutes until the top of the hour. So, yeah, let me get this set up. So let me just talk about this part here. So this is like an example problem that we're going to use. So all the programs that will run for these exercises come from this 4Pi project that I started putting together, I don't know, 5 years ago now, maybe, which I haven't really added much lately, but I probably should at some point. But one of the main example program here is this Monte Carlo program that estimates pi, right? And so the idea is each program um, implements this Monte Carlo algorithm where you take an area of a square and an area of a circle, and you sort of randomly throw darts at this target, right? And then you just count the number of uh, hits inside the circle and the number outside the circle, And if you just do the geometry, you get a way to calculate pi by just counting up the number of times the random selection ends up inside or outside the circle, right? So that's all of these programs are doing. It's a nice example program because it's pretty easy to understand, right? Basic geometry. Um, it allows you to play around with the parallelization aspects because it's basically what we would call an embarrassingly parallel program. So you can do all sorts of basic, parallel computing tasks and teaching stuff with that. And yeah, and then the programs aren't too long, so it's just very, very easy to understand. And so that's what we're going to use today as the example problem. So that's each time we run one of these, that's what's going on under the hood. We're not going to really look at what's going on under the hood. We're just going to run the program, get the answer, and uh, basically do measure some run times and things if you want as well. And that's sort of the idea. Because what we're really interested in is looking at how do we start looking at processes and threads and using top when we're running applications on these systems. Now, before I begin and jump into the actual exercises and get things set up, you might ask the question is like, okay, well, if we're just going to run this on like my local system, what does this have to do with like running on a supercomputer? Well, as I said, even though the HPC compute nodes are a little bit more um, specialized, where they have two CPU sockets, each CPU has multiple cores, they might have GPU acceleration behind that, specialized network cards and things like that. At the end of the day, when you start talking about just running programs and interacting with processes, right? That looks the same when you're on an HPC system as it would when you're running this on, say, your laptop, right? You'll only have a single processor, a couple of cores. I think I have maybe four on mine. Um, and so it's definitely a smaller scale, but the mechanics of the things that you can do to start understanding how to interact with top and running applications, some of the command line tools we'll use, it's all the same, right? And it's useful to understand how to do this because when you're on an HPC system like Expanse, like we will next time with the batch job scheduling talk, um, you, you know, y usually you can log into each of these compute nodes and interact with it and run top and look, is my application actually running inside of my job on this system, right? And that's why it's important to understand just how to do these things. Um, Even though right now we're just not going to do it on an HPC system, you can just do it on your own computer as well, right? And this is how I learned myself before I even had access to a cluster. So it's just a useful set of skills and tools to understand how to start Unity with. And you don't have to log into an HPC system to learn how to do it. So, okay. I think, okay, so we got 20 minutes. So let me see how much I can get through. Now, the link here is to an older version of, sorry, I need to stop sharing and go full screen for this. So the link here is to this batch computing repo in my personal GitHub, but I was hoping to, I think this is the full share. Yes. I think we have full share now. Yes. Can someone confirm?
Yeah, full
Yes.
Yes, you
screen.
do. Okay, thank you. All right, so here's this. This link here is to the version of the talk I first gave a couple years ago. I'm still was hoping to have it migrated over today to the complex. So this GitHub complex organization is where we're sort of trying to consolidate all the material and put all the exercises. I failed at that, but this is the new one that I've started here to start migrating things over and cleaning things up. Um, so let me see. What do I, yeah, let me I'll probably make a quick edit here to make it easier on you all. When you're looking for doing the material yourself, you can either go to my batch computing one, that's fine, or come here once I just fix something here as we go. But the um, the things that you need before you begin these exercises yourself are really just access to a Linux-like operating system, right? So I have a list of what you really need. So I have a Linux operating system, so that's what I'm going to use today. If you're using a Mac, you basically have access to a Unix, Linux-like operating system, and all of the commands are mostly the same on Mac. There's a few you'll run into that aren't the same. We usually try to point those out as we go through exercises in complex because most of the commands are very similar. So if you're using a Mac, what you'll want to use if you haven't used the terminal application before, that's sort of the equivalent that I'll be using today on my system. If you're on Windows, my recommendation is always to look into getting your Windows subsystem for Linux set up so you can practice your Linux skills on your local system. That's probably the easiest way, I would say, for most Windows users to get access to a Linux system that they can practice on other than having to log into maybe one of the HPC systems you have access to. But there's also things like VirtualBox, which is allows you to run virtual machines, and so you can sort of run your own full Linux operating system in something like VirtualBox. It's not too hard to set up, but it's just kind of not necessary anymore. That's usually what we used to recommend on um, things like Windows before WSL. But yeah, anyway, those are that's just the minimum things you need to get started uh, once you want to do some of these exercises. So, okay, where to begin? Okay, so I'm gonna drop back here, and the exercises that I'm going to do today. I'm gonna just make some edits on the fly so it doesn't confuse people too much. Just come. Let me. How do I? Forget what the markdown. Is that a comment markdown? I forget. Okay. Um, are from this link here. So I'll have it in both places. But essentially, if you go to the batch computing tutorial, it's just this first one on managing Linux processes is kind of the set of exercises I'm trying to consolidate uh, for this talk. And that's a familiar picture. That's the example program. And yeah, this is kind of the setup. So we'll walk through this now. Let me just get this out of the way. Try to increase my font. So I turned off Zoom. Okay, so hopefully that's a good enough text size. And then here's my terminal application I've opened. And now I'm ready. So I have my terminal. I'm just in my home directory here. Let me delete that. And let me go into the Scratch directory just to keep things a little clean. Okay, so there's a little bit of a setup that you get started. You just need to download this 4Pi repo that we're going to use for the examples. So that's the 4Pi repository. There's, again, different versions of essentially the same program that you can take a look at. There's Fortran, C, Bash, Python. But we're going to use the Python version for the exercises here. And so if I go into the Python folder, see we have the PyPy application. You can kind of see what the options are by running the help command. Basically, there's just a couple of options that aren't really too useful, and there's only one input value, which is the number of samples that we're going to run. That's why this is a nice problem. It's also very easy to scale how long your demo can run by the number of samples. So another reason why it's a good teaching tool. It's not a terribly interesting problem, but it's easy to sort of scale things to what you need for the demonstrations. Okay, so to use the program for the first time, we're just going to run the command with, or run the program with a million samples. And I'll let that run. And you can see that was pretty quick. And there, the output is my estimate of pi, right? So that's sort of the structure of these exercises. I try to just have a section with a command and an output, and so hopefully you can replicate that on your system as well. In a lot of the work that I do, I'm doing a lot of benchmarking work. So this next section on measuring runtime, I usually just use the time command, which is just something you can add on to any time you execute a program in Linux, or a command or anything. You can just put time -p. I prefer the -p, and it outputs this additional timing data at the end of the standard output. Usually I only care mostly about the real time. This is the actual wall clock time that has passed, how long it took to run the program when doing benchmarking, but won't go into the details of the other two metrics here right now. Okay, but they might be useful in certain cases. You can take a look at the time command for more information. Okay, 15 minutes. Okay, so now that we have our example program ready, it's running, we kind of understand what it's doing, and we can even time how long it takes. It's kind of ready to go. So the first exercises here teach you about the difference between background and foreground processes. And this is very much related to the difference between batch computing and interactive computing, which is sort of, two paradigms that we discuss in the complex program, right? So this series about batch computing, there's a talk on interactive computing. It's very similar between background and foreground. So the foreground process is what we've been doing, what I did here in this example. I'm actively in real time interacting with my terminal, my shell, to run programs, right? I'm asking the computer, in real time, please run my PyPy program with this inputs and tell me how long it took to run, right? That's the thing I asked it to do. This is running as a foreground process right now, right? So I'm directly communicating with the system. In contrast, a background process is when you're running the program without any user interaction, which is the equivalent of like how we run batch jobs on an HPC system, right? That you submit the job to the system and let it go and run, and hopefully you get some output for the research you're trying to do, right? So the background process is very similar in that you basically set it up, launch it, and hopefully it just sort of runs in the background without any need for further input from the user, right? So that's sort of the main, there is this difference between, so okay, we know what a process is, but there's differences between when you run a process, sort of what it looks like on the system, and sort of what the expectations are in terms of inputs and outputs, and yeah, that's sort of but the big thing is the interactivity, right? A background process is something you sort of want to shove into the background and just let it sort of churn away there for a while, right? So before I had like access to a cluster, I used to run a lot of my sort of science workloads on sort of just workstations in the lab, and we just set up those applications and run them in the background on the workstations we had, right? There wasn't any sort of centralized scheduler. You just kind of log in and just let it go. So that's what we're going to do in this first set of exercises. As we go through that, I'll be looking at sort of what's going on with the top command. So this is, again, the top command I mentioned. I'll just run that here because I'll have processes running. You can see my number one right now is Zoom, which is not surprising. And as I mentioned, it's like most of our sort of desktop applications are likely multi-threaded. Well, we can see here that, well, there's definitely more than one CPU being used by Zoom at this time, right? So this CPU column is the sort of the number of it's sort of well, so 100% usually means that that application is utilizing 100% of one CPU core. So here it looks like it's using about 2.5 CPU cores on my system and about 6% of the overall system memory that's available, right? Again, you can see up top here, overall system metrics as well. Like I have 32 gigabytes on this system. I have about 4 gigs free, 25 being used. There's more detail and nuance to these other things like the buffer cache and free used, yeah, which we won't get into. But you can see top gives you a lot of information about the things that are running, right? And that's what we're sort of interested in because usually when you launch your science application, even if it's on your local system, and especially if you're trying to, run sort of some parallel application, you want to maybe inspect how much its resources using. If you've asked the application to use 2.5 cores or 3 cores, and it's utilizing 2.5, that's usually an important metric for you to understand in terms of your performance, right? And the parallel scalability of the code per se. But you can also see there's other things, other columns here that might be of interest, right? So there's with processes, you can see on the very left-hand side, there's something called the PID. So this is the process ID. Next week, we'll see that every Slurm job gets a Slurm job ID. Well, on every node and on Expanse, once your application launches, it's going to look like a process like this, and it's going to have a PID or a set of PIDs maybe on the system as well. So that's why understanding this view into what's going on locally on a single node is useful even on an HPC system. Okay. And then there's other columns here, which we'll talk about in the exercise here. There's the priority, this column here with a lot of 20s you'll see, and the niceness, which is a lot of zeros you'll see there. And this controls essentially how the scheduler on my computer is prioritizing which applications at any given time, right? So these different values that you see popping up, it's like 9 and -11, 20 and 0, -51 and 0, those things mean something to the scheduler, right? They mean how they give a level of how much it needs to pay attention to those individual processes, essentially, right? And whether or not that they should have priority over others, right? It's a sort of a relative prioritization on these systems. Okay. So I think I've said enough there. I've got 7 minutes or so. So let's run a few of these exercises. Yeah, so I go through the details here a little bit. But there's tons of material. There's links to the top Wikipedia page. You can get more information as well there or in the manual. But let's demonstrate the difference between foreground and background processes. So this is the first thing that you'll usually want to understand how to do when you start running a program from the command line. So we'll just take our application here. I think I scaled up to what? It's 100 million or something. So it's going to run for a while, right? It's going to probably run longer than we have time left. So you can see that it's running, but I've lost sort of access to the shell won't respond to me, right? So this is, you know, because I'm running this program in the foreground, right? Basically, the shell that I'm using, the terminal, the actual, terminal there, um, has taken away control from me because I've ran this program in the foreground. So all of the sort of control from the shell is now focused on the program there, right? So what I need to do here, and is what you'll often do sometimes when you're playing around with your running your applications, right? You'll open up another terminal, another shell, and run the top command, right? And well, this is a little bit confusing because it still has my zoom showing. So let me go ahead and clear this out. And usually what you want to do is only look at the processes that you've started because there's a lot of background noise from the operating system and things, and maybe other users sometimes. So you only want to usually look at your processes. Unfortunately, it doesn't get rid of my zoom. There's ways to select on the actual command as well, but usually what you're going to use is a lot of the time is the -U option for the user view. And so you can see here, I have Zoom open, but now I have this kind of computationally intensive Python 3 process. Well, that's the program I started over here, right? This is the PyPy program that's actually running. So you can see here, it's usually utilizing basically one CPU core, which is about 100%, right? So it's running sort of flat out on a single CPU core. And this program, if you look at the details, yeah, it's not multi-threaded or anything. So it's just a serial implementation of this Monte Carlo algorithm. Um, and obviously, since it's just sort of counting numbers, random numbers and where they've fallen in that geometry, there's not a lot of memory usage. It's not a memory intensive application. So you can see that here. Um, yeah, and that's about all that's sort of interesting, I guess, about what that looks like in top right now, right? Now the question is that, okay, when you start a program like this, I made an oopsie and that this might run for, I don't know, 24 hours. And do I want to keep this running for 24 hours in the foreground here? Probably not. Um, let's, maybe reset the input parameters to my program. So let me, the first question becomes like, okay, how do I stop this, right? Because I don't have access to the terminal anymore, essentially, in that shell. So, you need to send what is called like a signal to the process, right? So how the operating system works in the hood, there's all these different types of signals and things that you can use, or that get used by different commands that you might use or different actions that you might take on the keyboard. And to send this interruption signal to the program, which tells the running process in that shell to stop, is just with the Control C. So sort of the cancel button, basically, right? And so if I do a Control C, which I just did on my keyboard, this is kind of what happens, right? So it drops out of the program, says, oh, you know, in Python, that's sort of a keyboard interrupt, right? So it throws that error essentially, like, well, yes, not really an error. I just says it confirms it. I quit the program from my keyboard. So yeah, so that's sort of what a foreground process looks like. Uh, yeah, and so you can see the output here from the, yeah, so you can see I try to label, yeah, terminal one, terminal two, so kind of what's going on in the exercises. But okay, so how do I background a processes? If I wanted to run that thing for 24 hours on my laptop per se, how would I do it? So the key thing usually you learn first when how to background a process is just to use this ampersand sign. So if you run a command on the run your application on the command line and want to put it into the background, you just add the ampersand sign to the end of that command that runs the program. So if I want to background the process, you can see here, the output is now simply this number, which we'll see in the top view over here, is the PID of that Python 3 process that I'm running, right? So that's sort of the job ID, right? The process ID of that command that I've started, right? And so it's just gonna run there until the application completes, right, in the background, or if something goes wrong on the system, right? Uh, yeah. And here, this example, so that's what this looks like. But you can see here now I have freedom to go and run other commands in that terminal, right? So basically, the control in that shell has been relinquished back to me because I just only put that process in the background, so I still now have foreground access to the system from this shell, right? So that's the difference, sort of in the feel of between what's the difference between a foreground and background process, right? I'll skip this since I'm at the top of the hour. But this is just another way to look at the top command with some a little bit more fancy bash in there. But you know, because it sort of selects the last process that was started essentially, and so that's what this command is doing. Um, but the just to complete maybe this first set of exercises on foreground versus background, right? Now the question, just like we had in the foreground process, is like, okay, uh, maybe I realized a couple hours in that I made a mistake and I don't want that program to run anymore because I started checking the output files that are being generated and it's not working correctly. And so I just want to kill it so I can get that core back because it's using, one of my CPU cores that is not useful. So how do you stop that background process? So the most common way that you learn how to do this is with the kill command. So it's very simple. Usually there's options and things and reason why you might use some of the options. But in general, when you're first starting out, all you need to use is the kill command with copy and paste with the process ID that you want to kill. So let's not copy and paste the zoom command. That would not be a good end to this session. Um, uh, so yeah, all you have to do is run the kill command with the PID that you want to get killed. And we should see once I hit enter here, on top, we'll see my Python 3 process go away. And boom. You also get back we don't get the results from the program because I don't have like an intermediate output and estimate of pi that gets popped out. But you see how long the program was running, a couple minutes while I was talking. But you see you get the terminated signal back, and that's what it does, right? So it's, again, the kill command, just like Control C sends a signal to the process. It says, hey, do this. Usually, hey, stop. And that's what happens. So yeah, the program exited. You can start like looking at the details here. There's things like exit codes, and those things mean something of how the process was stopped and how it was killed and things like that. Or if your program fails, those things matter as well. Um, but that's sort of the initial sort of set of exercises that are available here in this tutorial that are also getting migrated over to the complex uh, main page. But fortunately, I didn't get that there. So there's a few other exercises you can walk through here. If you want to go further and look at some of the other exercises in this batch computing repo that I have on my personal GitHub, feel free. But that's sort of the end for today since we're a couple minutes over. So I'll stop there and take questions once Cindy's, I think, done recording.